confirm if you can hear me clearly.
Yes, sir.
Yeah.
Okay, thank you so much. I want to welcome everyone to my lecture today. And of course, this is going to be the second week of a lecture in this summer semester. And I want to use this opportunity to inform you that the assignment 1 has already been uploaded. Now we advise that you check the module for information. Okay, so like I said, assignment 1 has already been uploaded. I will advise that you check the course module for information. Today, I'm actually going to walk you through an exciting statistical topic. Give me 1 second. I'm actually going to share my screen. Okay, so the focus today is basically expectation on the finite sample space is part 2. We started this last week, and of course, we're basically going to finish that today. Today, the outline, I'm actually going to walk you through the change of variable. By change of variable, of course, we started with a particular discrete random variable with a probability mass function. We basically want to, concentrate on another new variable, which is a function of the old one. And of course, we basically going to learn how we can actually seek for the probability mass function of the new variable. Don't forget, the new variable is basically going to be a function of the old variable. So, and that is the reason why I said we are going to get a probability mass function for the new variable, which is expressed as a function of the old variable. Now, lastly today, I'm also going to walk you through what I call the concept of independence and what is the role played by Cartesian products. Okay, what is the role played by Cartesian products in this? Of course, I'm actually going to walk you through that as well. So let's get started. Okay, you remember last week I actually walk you through the probability mass function and the corresponding expectation of X. Okay, now just trying to remind you of what we actually did last week, and we use that in everyday philosophy. Okay, just to remind you of that. Okay, so going into the change of variable now, like I said, we actually going to start from the original variable X. Okay, and you know what? The original variable X has a support, which we call a space of X, and the probability mass function exists for that. I told you, when you have a sample space, of course, the probability, mass function exists for that. Okay, particularly we use that for a discrete random variable. And you know what? If we basically have a new variable, the new variable that we have right now is actually Y. Don't forget, the old variable was actually X, but you know what? The new variable is a function of the old one. And that is why you see Y equal to G of X. Now, you know what we want to do now? We know the probability mass function of X. We know the probability mass function of the old variable. Now we are seeking right now to obtain the probability mass function for the new variable Y. And don't forget, the new variable Y actually depends on the old variable X. Okay, so what we are seeking now is actually to get the probability mass function for the new variable. And don't forget, each of them is actually discrete. The old variable is discrete and the new variable is also discrete. So when you take a look at this now, we basically want to find the f of y. When we're seeking to get the probability mass function for the new variable y, which happen to be a function of your variable x. If you want to do that, this is what we're actually seeking. Okay, we basically want to find the f of y, which is equal to the probability of a random variable y, a new variable y, equal to a realized value y. Okay, and if we want to do that, okay, you don't forget that we said the other time y equal to g of x, right? So it's like here we are plugging in, okay, g of x, right? When we plug in g of x, that is exactly what we're doing here. Okay, when you plug in g of x, okay, and you basically have that, okay, then it's more or less like you're actually summing over x, because summing the sample space over x is actually mean you basically want to get the probability of y, which is the probability of the new variable. That's exactly what I'm trying to talk about. Okay, now the new variable, the probability distribution that we're now seeking now for the new variable is what we call the image distribution. I want you to take note of that. The probability distribution with the PMF of y, we call that image distribution of the distribution with PMF f of x. Don't forget, initially, this is the function. The f of x is basically the probability mass function of the old variable x, but now we actually seeking the probability mass function for the new variable y. And don't forget the new variable y actually is expressed as a function of a old variable x. And therefore, the moment we're able to get the probability mass function of the new variable y, we basically call that the image distribution. That is exactly what I'm saying. And you know what? The y, okay, is actually going to be taking values in a t, okay, that which is actually going to serve as a sample space for the new variable. Okay, so that is exactly what I'm trying to define here. And of course, somebody said, what does f of y represent? It represents the probability mass function of the variable y, the probability mass function of the variable y, which is the new variable. Okay, the old variable was x, and don't forget, the new variable is expressed as a function of the old variable. So what I'm going to do now for you to really understand what I'm talking about, I'm basically going to use the idea of domain to codomain that I walked you through the other time. I'm going to show you now. Take a look at this. We got x1, x2, x3, x4. Take a look at that. But when you take a look at this, you're basically going to see that you have x1, x2, x3. So equal to y1, which means the y1, the f of y1 is being expressed as a function of old variable in this situation now, x1, x2, x3, they are the old variables. And you know what? The new variable y1, the new variable y1 is being expressed as a function of the old variable. That is exactly what you're saying here. So what you're saying here is all like, okay, the f of x1 plus the f of x2 plus the f of x3 must be equal to f of y1. If you take a look at this situation is what we call many to one. Look at that, many. You got x1, x2, x3, and that actually go to one. Take a look at that. But when you take a look at this guy here, there is nothing in the domain that comes to that. That was why you see f of y2 equal to 0. When you see for y3, there's no connection, with any of the elements in the domain. Because of that, the f of y3 will be equal to 0. But when you take a look at the last one now, which is this guy now, okay, then in that kind of situation, that is looking like a one-to-one stuff. If you see x4 to y4, one element in domain is being mapped to elements in the codomain. That is that is this guy here, which is a one-to-one stuff. So take a look at that. That is the kind of situation we're basically going to have. But you know what? We're actually in statistical analysis. We have what we call the change of variable. We could have a situation where, the probability mass function of the old variable, or maybe assume a name like a uniform. And we basically, if you take a look at the explanation here now, we have x and y. They are bivariate, okay? X actually taking values in that, and y also taking values in that. And when I'm considering the x and y, okay, of course, I'm actually going to say take values in that. For instance, if I go to x, y, z, okay, that is going to be taking values in that repository. So I just wanted to take note of that. Now take a look at this range now. Okay, you have the whole thing lie between 0 and 4, but y is less or equal to x. In this kind of situation, you may actually, we want to find what are the distribution induced by the natural projection. Take a look at this. We want to go from x, y to just x. Okay, here this is saying you want to go from x, y to just y. Okay, we have a way to investigate that in statistical analysis, where I started with two variable situation. I started with a bivariate, and I want to go from bivariate to just univariate. Of course, in statistical analysis, there's something we're still going to talk about situation where we have a joint distribution, and we want to go from joint distribution to marginal. Okay, maybe you have a f of x, y, and we basically want to find the probability function associated with x only, or we want to find the probability function associated with y only. That's a marginal. We call that a marginal. Okay, the marginal distribution that we're still going to talk about as far as discuss is concerned. Okay, now if you take a look at this is one-to-one that I talked about the other time. Okay, I'm going to show you right now. Okay, this guy now. This is a one-to-one. Okay, I think the one-to-one in mathematics, they call that injective. I think they call that injective, talking about one-to-one situation. Okay, now the one-to-one now, if under the one-to-one, we're basically going to have, this kind of situation. Look at that. Okay, and you know what? The only situation where f of y will be equal to 0, that is when y is not equal to g of x. Don't forget what we're considering now. We are considering situation where y is a function of x, which is this guy here. This is the one we're considering. Y is a function of x. Don't forget, x is an old variable, y is a new variable. In that kind of situation, we're basically going to have this guy here. Okay, but situation where y is not, okay, then f of y will be 0. That's exactly what I demonstrated. If you take a look at the domain and the codomain structure here, that actually applies to that guy there. That is not, one-on-one situation. It means in this kind of situation now, you're trying to say y is not equal to g of x. The new variable cannot be expressed as the old one. Okay, but the last one, which is this guy here, the new variable can actually be expressed as the old one. I'm basically going to walk you through an example right now. Okay, I'm going to walk you through an example right now. Give me 1 second. Let me see if I can. I'm going to have a space to do that. I'm going to stop my share now. And you know what? I'm basically going to use my whiteboard. Give me 1 second. Let me just enable me. Want to share something now. Okay, so I'm actually, give me 1 second. I'm sharing now. I'm going to give an example on how that can actually, you know, be done. Okay, so if you are trying to see my whiteboard now, you need to be able to tell me, can you confirm if you basically
Yes.
see my, okay, thank you so much. Thank you for confirming that. Now, I want us to have an example now on a of change of variable. Okay, now take a look at this. If I have a random variable x, okay, follows bin, okay, when you say bin, we talk about binomial, binomial. Okay, if I have a 3 half, what does that mean? You remember what we did the other time when we were dealing with the Bernoulli? Okay, the general formula is basically this guy here, n and p. Okay, this is binomial, right? This is binomial. But you know what? When n equal to 1, when n equal to 1, okay, then x is going to be distributed binomially 1p, or you can just say binomial 1p. There's no problem. In fact, here they can also write, you can just write this as binomially p, because of the fact that we know that one trier is Bernoulli, but more than one trier is binomial. I'm going to tell you the difference between the two now, because we basically, I want to use this as an example in the change of variable. I'm going to say this again, whether binomial or Bernoulli, we use that as a probability distribution to model dichotomous outcome. Okay, when you perform an experiment and there's only two possible outcome, we use either binomial or Bernoulli. But the difference between Bernoulli and binomial is that in Bernoulli we have one trial. Okay, one trial, but in binomial we have many trials. So right now the situation I actually want to define is binomial, because I want to have more than one trial and I still want to have two possible outcomes. Okay, so what I'm going to do now, the example I actually want to cite it, okay, uh, it's actually going to come from binomial, okay? Like I said right now, we're going to be focusing on the probability of a discrete type. Okay, the change of variable we're going to be talking about now is going to be of discrete type. Okay, now take a look at this guy now. If I have x followed by binomial, now you know 3.5. What does that mean? N equal to 3 and P equal to half. Now, this is the situation now. I basically want to toss a fair coin 3 times. Okay, I want to toss a fair coin 3 times. Okay, now if I want to toss a fair coin 3 times, okay, I need a sample space for that, right? Take a look at this. I got H and T, right? Using a tree diagram, I'm going to have that guy, right? H and T. Okay, if I go again, I'm going to have HT. Okay, HT, another HT, then HT. Now, if I want to write my sample space now, you know what I've done here? This is like flipping a coin. Okay, we are flipping. Okay, we are flipping a fair coin. Okay, we are flipping a fair coin 3 times. Okay, that was why you see n equal to 3. And when you are flipping a fair coin 3 times, there's a natural probability that actually exists. Until you know that, the natural probability that exists is half. The probability, if it's a fair coin, the probability of any size showing up, since we got two sides, is basically going to be half. So right now, if I want to write a sample space, of course, I'm basically going to write, of course, head, head, okay, head, head, tail, right? Head, tail, head, right? Head, tail, tail, right? Tail, head, head, right? Tail, head, tail, right? So tail, head, tail. So tail, tail, head, and tail, tail, tail. Now take a look at that. That is going to be the possible, that is a sample space. Okay. Now, is there anyone in this class right now who doesn't know how I figure out this, how I got the sample space to be this? Is there anyone who need clarification on that? Can you all confirm again? If you are hearing me clearly, is everyone in this class right now hearing me clearly?
Yes, sir.
Okay, thank you so much. Now, if you're really enjoying this now, if you really understand this concept now, I need you to comment yes, or you say yes. Okay, thank you so much. Like I said, do not hide your feeling. Now, we are dealing, the X here now is the old variable X, right? Now, we need a probability associated with the X now, PMF. Okay, now, if you take a look at the sample space that we have, if I want to set up a probability for that, okay, don't forget, I actually want to have events with their corresponding probability. Now, the question now, I need a support. What is the support of X? Okay, the support of X, the interest is basically on the numbers of head, right? Numbers of head. Okay, here head is going to be 3, right? Head is going to be 2, right? Head is going to be 2 here, right? Head is going to be 1. Head is going to be 2. Head is going to be 1. Head is going to be 1. And head is going to be 0. Now, when you want to look at the support of random variable X, now, when I say support of X in this situation, I'm referring to the possible value X can take, which is also called space of X. We also call that space of X. Now, the possible values S can take now is 0, 1, 2, and 3. Okay. Now, what is the probability of 0? Okay, the probability of 0 is having 30. That would be going to be 1 over 8. Right now, I want to find the probability of X, right? So what is the probability of 1? That would be 3 over 8, because why do you say 3 over 8? Okay, we got 1 here, 1 head here, 1 head here, 1 head here, right? What is the probability of 2? That is 3 over 8. What is the probability of 3? That is 1 over 8. Now, do you know what I have now? What I have in this table now is what we call the PMF of X, which we call the f of X, which is the PMF, the probability mass function of the original values of X. Now, if I have this now, let us now assume that we now want to define a new random variable, based on this table now. Okay, based on the table that we have now. Okay, we now want to have a new random variable now. Give me 1 second. I'm actually going to clear my screen now. Okay, so let me clean this one. Okay, so if I this is what we have now, right? This is 1, 0. Okay, now if we now define, okay, suppose, okay, suppose we want, okay, to define a new variable, and that variable now is y, which is equal to 2x minus 1. Look at that. We want to define a new variable. Oh, give me 1 second. We basically want to define a new variable. You can see here, this is more or less that we have y equal to g of s that I mentioned the other time. Okay. Now, if you want to define a new variable now, and you know what? And we basically want to find the PMF of the new variable. What we're doing is a change of variable. Okay. What we're doing is a change of variable. So now what I'm going to do now, okay, uh, since my y is actually equal to 2x minus 1, okay, now what I want to find, I need the probability of y equal to small y. This is what we're seeking now. Okay, you already know the probability mass function of the old variable x, which is the one that we have in the table here. When you toss a coin 3 times, a fair coin 3 times. But right now, the question now is, we need to find the PMF of y, where y is a function of x. We have a y equal to 2x minus 1 right now. So what are we going to do? Okay, so the probability of a random variable y given that, okay, is basically going to be 2x minus 1 equal to this. Don't forget, I'm actually substituting this guy now for y, because you're told that y equal to that. Now you can try to solve, you can continue solving the problem now. Okay, solving the problem now. You basically going to have, uh, you know, if you look at the probability of 2x minus 1 equal to y, okay, if you want to solve for x, what are you going to get? So it's basically going to be, you have 2s equal to y plus 1, and at the end of the day, you're going to have y plus 1 divided by 2. Now, you know what happened here? It means before we can actually get x, okay, the x here, it means we added y to 1 divided by 2 to be able to have the space of hairs that I talked about the other time, which is from 0 to 3. Okay, now what we're going to do now, we actually going to set up a domain. Take a look at what we're going to set up right now. We're going to set up a domain of x, right? What is the space of x? 0, 1, 2, 3. We're going to set up a codomain. Don't forget, we actually want to map. Okay, your y is going to be 2x minus 1. Oh my God. Now, you want to map that into the new domain now. Okay, that's exactly what you want to do. And you know what? You basically, using this guy to map, I can just basically write this guy is actually, you know, going to 2x minus 1. You're initially in x. Don't forget, this is going to be your new y, right? Okay, if I'm going to plug in 0 into that 2x, that's going to be minus 1. Then you're going to plug in 1. That's going to be 1. Plug in 2. 2 times 2 is 4, right? 4 minus 1, 3. 2 times 3 is 6. 6 minus 1, 5. So what do you have now? You basically have 1 to 1, right? Take a look at that. That is 1 to 1 mapping. That is what you are, which I call injecting. Look at that. That is exactly what you have now, which is what I was trying to explain to you. Now here, this is a possible, here you got the possible values of x, possible values of x, okay? And here you basically have possible values of y, possible values of y. Now, do you know what we've just done now? Okay, we've just created the support for y, which is the possible values for y, which is minus 1, 1, 3, and 5. Do you know the next thing we're going to do with this one now? We'll be able to obtain the probability mass function for that. Don't forget, well, in the change of variable, we actually want to find the probability mass function for the new variable. But before we can do that, we need to first have some elements in the new variable. Now, the element in the new variable is actually minus 1, 1, 3, and 5. The element in the old variable is 0 to 3. Now, if I now want to find, the probability value associated with each value in the new variable, what am I going to do? Give me 1 second. What I want to find is this. I basically want to find what is the probability of y equal to minus 1. Okay, the first guy here. Okay, and if I want to find that, don't forget, what is your y? 2x minus 1. Okay, we don't say equal to minus 1. Don't forget this guy. That is the function we're using, right? Now, when you take a look at this now, when you want to solve that, what do you think that guy is going to give you now? You're basically going to have the probability of 2x, right? Equal to 0, right? Okay, when you have the probability of that equal to 0, okay, so what are you going to have? So it means like you have the probability of x equal to 0. And what is the probability of x equal to 0? Do you remember when we did the other time? Let me remind you the one for x that we did. Don't forget when we have x, p of x, 0, 1, 2, 3. Okay, somebody said 1 over 8. Good job. So 3 over 8, 3 over 8, 1 over 8 automatically. So this is going to be 1 over 8. Look at that. So you just find out for the probability of y equal to minus 1. Okay, so the probability of y equal to minus 1 will automatically give you the probability of s equal to 0. Just take a look at that. Okay, you do the same. okay, for the probability of, y equal to 1, okay? Don't forget the probability of y equal to 1 will be 2x minus 1 equal to 1. And that is going to be 2s, the probability of 2s equal to 2, which is going to be probability of s equal to 1, okay? So the probability of x equal to 1, okay, is 3 over 8, okay? So you're going to do that too. So you continue doing that, finding the probability of y equal to 3 and y equal to 5, okay? So give me 1 second. I'm going to clean up this guy now so that you'll be able to have space. So we've done for y equal to 1, you're going to do for y equal to 3 and y equal to 5. So similarly, you're going to do for y equal to 3, you're going to do for y equal to 5, okay? So, and if you do for y equal to 3, of course, that will give you 3 over 8. And if you do for y equal to 5, you're basically going to have that. Don't forget, if you want to do for y equal to 3, okay, don't forget you actually have 2x minus 1, okay, equal to 3. So which is basically going to be 2x equal to 4. And which is going to be x equal to 2. So which is the probability of y equal to 3 is the same thing as probability of s equal to 2. So which is 3 over 8. Okay. Now, finally, when you now compute that, finally, you're basically going to have this now. This is going to be a new table that you're basically going to have. Okay. The new table that you're basically going to have, okay, is going to be y, the probability of y equal to y, and you have to forget minus 1, okay, the possible values in y that you actually got. So minus 1, 1, 3, and 5. And of course, the first one, you're going to have 1 over 8, 3 over 8, then 3 over 8, and 1 over 8. Now, this is a PMF of the new variable y. Y, the guy here, is a PMF of the old variable x. So take a look at that. You can see there's a difference between the two. So right now, I've just given you the example of how to do the change of variable for discrete random variable. And the experiment that was performed initially is when you toss a coin 3 times, okay? You toss a coin 3 times, okay? That is the example that we do that right now. Is there anyone who have any question to ask about the example that I use in this change of variable before I move on? Is there anyone? Okay, if you are fantastic, like if you really understand what I just pass across right now, I need you to say yes or you comment yes. Okay, thank you so much for that. Now, let me tell you this. Do you know that several questions can be asked or, on this now, where examiner can actually ask you to find the expected value of y, expected value of s, okay? Now, if they can ask you to find the expected value of y, you can find the expected value of x as well. Take a look at that. If you want to find, don't forget, there's going to be summation x, okay, f of x, but this is going to be summation y, f of y, okay? So if I want to find the expected value of x, okay, this one, I'm actually going to use this table here for x, where I'm going to multiply in that, what you did last week, then you had up. But if you want to find the expected value of y, then you got to come to the new table, okay? There's possibility that you could get a different mean and different mean and different variance for them. Okay. And additionally, what I'm going to add, you can also have, if you ask to find the variance of x, expected value of x squared minus expected value of x or squared. Okay. Though there's a difference between the expected value of x squared and the expected value of x or squared. And they can also ask you to find the variance of y. Okay. Now that is going to be,
Professor,
okay, go ahead.
can you rewrite that last equation at the bottom of the screen? I couldn't see it just because of how Zoom is set up.
Oh, okay. I'm gonna rewrite that now. So you mean you mean this guy here? Is that what you mean, right? The one I'm writing now? Can you see that?
Yes, that was the one.
Then the expected value of y. Okay, p of y. And you know what? Expected value of x squared is just basically going to be, I need to square that first, and expected value of y squared, then I need to square y. Don't forget I have to use that. And, I can find the variance now. Like if I want to find the variance of x, it's just basically going to be the expected value of x squared minus expected value of x all squared. And similarly, I can also say that I want to find the variance of y. So which is going to be expected value of y squared minus expected value of y all squared. Now, can you see that now, right?
Yes, sir. Thank you.
Okay, you're welcome. So you can take a screenshot, of this explanation. Okay,
Okay.
so okay,
Uh,
go ahead.
for the expected value of y, is that the summation of y times p of y, or is it the summation of x times p of y?
Oh, I think I made a mistake here. Sorry about that. So I think this is what you're trying to say. They are going to be y all true for y, and they're all going to be x all true for s. So thanks for catching that. So that's a mistake by me. Okay, so I think you can see that now. Okay, now I'm gonna stop my share now. Then I'm gonna go back to the material. So that is how to deal with the variable, the change of variable uh as far as the discrete is concerned. We're still gonna do that for continuous, okay, variable. We're still gonna do that. Okay. Now uh I'll quickly go into a different thing now, uh, which I basically, give me 1 second. Um, okay, let me just come here now. Let me come to uh, situation. Now, this is what I was trying to say about the expected value of y, the formula that I gave you the other time. Okay, for that, I think that should be easy for you now. Okay, and you know what? If x and y are equal in distribution, we expect that the expected value of g of x, okay, should be equal to the expected value of g of y, the g of x. Okay, I think a chart came in. Let me read my chart. Uh, let me see. Oh, okay. Okay, I think there's no chart. Okay, I thought a chart came in, but there's no chart. Okay, so this is going to hold. Expected value of g of x is going to be g of y. Okay, so that is what we mean. Okay, so I quickly want to situation where you have x and y, particularly at time we could have a joint distribution. Okay, this is like a joint distribution of x and y. Okay, we are you know where x can take a value, x and y can take on values, and where x and y actually lies in that. Let me first tell you this. If you take a look at the statement here, you're basically going to see we have a random variable x that is taking values in this finite subset x, okay, of a real number, and you have a random variable y also taking a values in the finite subset t. Okay, so the space of x is different from the space of y. Right now, the space of x, we're talking about the subset x using that one and t for y. Okay, I just wanted to take note of that. Okay, now the change of variable that we just discussed is more or less like crossing x with t, the two finite subset where x and y are taking values. Okay, and automatically that will go to real number, right? Okay, which we can also call the probability mass function of a two-dimensional random vector. Okay, okay. The same thing also if I have for three variables. I'm only just going to have this guy now. Okay, I'm just going to have this. Okay, and in that situation, I'm actually going to have XYZ. Okay, lies in this. Maybe I can say M, where the final subset of X is this, final subset of Y is that, and that of that guy is this. Okay, we can also have it just for information. Okay, now if you want to generalize, okay, where we have x1 up to xn taking values in the final subset, okay, this final subset of x1 is this, the final subset of this is this, up, and that one is that. Okay, and if I want to have the joint, that's a joint, like f of x1 up to xn, okay, which is basically going to be equal to that, right? Okay, where x1 up to xn actually lies in the cross product of that. So that's a generalization of the whole thing. Okay, that's a generalization. Okay, and of course, just like what we did the other time for two variables, okay, where they have equal distribution, okay, for so many variables, of course, the expected value of g of x1 up to xn will also be equal to that of g of y1 up to yn, okay, for equal distribution. I just wanted to take note of that. Okay, our last objective today is independence. In statistical analysis, independence is very, very important. Okay, somebody, let me see, I think a chat came in. Somebody said, does S times T means S star T? Oh, okay. I think I'm going to explain that now. Because of that, because of the question somebody has in the chat, the person was asking about this, whether it is the same thing as this. Of course, I'm actually going to explain that. That's what we call Cartesian products. So which I'm basically going to give you, and because we need to understand, for us to understand independence, Cartesian products actually play a huge role. Okay, so I'm going to answer that question with when I'm doing Cartesian product. And somebody said, when would a change of variable be helpful in real life? Oh my God, that's a very, very good question. You know, in economic analysis, okay, in economic analysis, you know, you could have a situation where you, excuse me, where you basically have a particular function. Maybe it could be a supply function, and you now realize another function, a new variable, maybe a total function or something, could actually be depending on another functions. So in real life practical situation, this is very, very useful. Also useful in physics, where you talk about the rate of change, where, you know, for instance, if you have um, a distance function, okay, you have a distance function and you differentiate distance, you have velocity, right? You have velocity, you know, when you differentiate distance with respect to time, when you take the derivative of a distance function with respect to time, that gives you velocity, right? And you know what? Velocity again also depend if I want to get acceleration, okay, when I differentiate velocity with respect to time, okay, that will give me acceleration. And don't forget, acceleration is a function of velocity. Velocity is a function of a time. Look at that. That's a change of variable. Okay, so change of variable has application in economics, in physics, and so on like that. Okay, I think the person that has that question, you made my day, because I told you the other time that, you know, you need to know, you know, what happened, you know, the connection to real life. So thank you so much for asking me that question. You've really done a great job. Okay, now, for me to be able to explain the concept of independence, I'm going to talk about Cartesian products. You know, uh, because before we can say variables are independent, okay, the support, it has to be the support of the Cartesian products. What do we mean? When I say Cartesian products, okay, Cartesian products, what do I mean by that? The Cartesian product is talking about the product of ordered paired. Okay, for instance, if I have X, okay, maybe I have 1, 2, and I have Y, and Y is probably 3, 4. Okay, and I want to find the Cartesian product of X and Y, which is X times Y, or X times Y. Okay, you know, somebody asked a question the other time whether they are equal. Yes, you could use it's a multiplication sign, or you can use that. There's no problem about that. Okay, you get what I mean. Okay, now let me just give me 1 second. Now, if I want to get that, okay, I'm basically going to have 1, 1, 3, okay, 1, 4, okay, 2, 3, okay, 2, 4, okay? That is the Cartesian product of X and Y. Okay, if I want to define that, if I want to mathematically, if I want to define that, I'm going to say X and Y such that X actually take values in that and Y takes values in that. Okay, so the product now, we actually give you different kinds of, product that can be, that you can have, and they have to be ordered. Okay, now this is what we mean by Cartesian product. But let me tell you, S times Y is not going to be the same as Y times X. There's no, commutativity does not hold in Cartesian products. Okay, so if you cross X against Y, it's different from crossing Y. If you cross Y against X, now it's going to be 3, 1, 3, 2, 4, 1, 4, 2. That is different from this guy here. Now, where am I going? We are interested in the the cardinality of a Cartesian product. Okay, like for instance, if I have the cardinality of S cross Y, okay, mathematically it should be cardinality of X multiplied by cardinality of Y. The other time I gave you 1, 2, example 1, 2, and 3, 4. What is the cardinality of a set? Okay, cardinality, okay, cardinality. So that is the sign. The cardinality of a set actually means the number of elements in that set. I'm going to say that again. The cardinality of a set means the number of elements in that set. Okay, now, what is the cardinality of X? Yeah, how many elements? 2. What is the cardinality of Y? How many elements? 2. Okay, and the other, but when you cross that, you remember, let's see, when you cross that the other time, don't forget you have 1, 3, 1, 3, 1, 4, 2, 3, 2, 4. Now, what is the cardinality of this? The cardinality of S cross Y is 4. And take a look at this. 2 times 2 will give you 4. So what have we established? We have established this rule. The cardinality of S times Y, the cardinality of 2 non-empty sets. Okay, I'm going to say that again. The cardinality of 2 non-empty sets is equal to the product of the cardinality of the respective set. Okay, and you know what? This is exactly what we need in the independence. Because the independence of a random variable, we basically want to establish the fact that the probability of a joint of random variable can be written as a product of the marginals. And that is the reason why cardinality actually play a role in the independence. Okay, the condition for independence is that the support of the support of the cardinality should exist. When the support of the Cartesian product, when the support of the Cartesian product between the two variables exists, then we can say the two variables are independent. I'm going to say that again. And that's exactly what I'm trying to talk about here. Okay. And that is what we mean here. But oh my God, my time is up. You know what? I don't want to rush you. I'm basically going to start from here tomorrow. I don't want to rush you at all, because I really I want you to understand every bit of this particular course, because the Cartesian products play a huge role in independence. So I can assure you, I will start from here tomorrow. Is there anyone who want to ask question or who need clarification before I go today? Is there anyone? Okay, if you really understand the message that I've passed across today, I need you to say yes, or you comment yes, if you really understand what I've explained today. Oh my God, look at me, look at me. I'm so happy. Okay, I'm so happy. But you know what? If there's anyone who doesn't understand, please, okay, send me a message. I'm actually going to walk you one-on-one during my office hour. You pay for the service, you deserve to be solved better. Okay, I want to appreciate everyone for attending my lecture today. I hope you guys enjoying it. Like I said, I'm gonna start from the independence tomorrow.